Welcome back. In this video I'll be solving a Leetcode problem 450, delete node in a binary search tree. So given a root node reference, we need to delete it and return the new root, and this is nothing too special. We also can have no nodes. I started filling this one, but my MacBook was in clamshell mode, so no sound. And let's do this again. Well, we have to do this with recursion because any other way I think it's too complicated. And if you know recursion, you know. If you don't, learn it, especially for this problem. Recursive solution. Understand it, of course, not learn by just to know it. But essentially, let's think recursively about this problem. So our first base case is we cannot find a node. So if not, or we don't have a root, and we came to delete some node. So if not root, we return root. That's our first case. So that's basically if there is no root, and also in recursive calls, if we get to place that we want to delete from some root some key and that root doesn't exist, we just return nothing, and nothing will be changed then. And now you'll see other calls. So next call is so we have to check what's the root value in comparison to the key. So if root dot key is greater than root dot value is greater than key, then we need to so we didn't find the target node. We have to go, since root value is bigger, we have to go to the root dot left and potentially update. So if we delete, let's say, root dot left, we'll need to update on this level root dot left to be so self dot node root dot left key. If you can get hold of this, then I think it all makes sense. So if our key is less than root value, we try to delete in the left subtree and we update the left subtree. Else if root value is less than key, then we need to do the update on the right subtree. So root dot right is equal to self dot delete node root dot right key. And let's stop here and imagine this key does not exist, and let's not consider a situation where it exists. So let's imagine I tried to delete 8. So root would be 5, and we have root, so we don't return. 8 is greater than, so it's this case. So in this call, we will update our root right with delete node root right key. So we do a new call where root is now 6. So we do the 6, and it's the same thing. So it's still less than a key. We do another call and we update root right. So now 6 right is updated with what we return from delete on the 6 dot right, so that's 7, key 8. So another call, we go to the 7, it's again the same thing, and we try to so it's still greater, and then we call self delete node root right key. But when we go to that call, we don't have a root and we return nothing. So root and root is nothing here, so 7 keeps nothing. And the thing I forgot here is to return the root. That's the catch here, because when we go to this call back, so on the call for the root is 7, we updated with nothing, and we returned 7 to the 6th call of root, right, and so on. So I think you get the point. And when you think about it, it's pretty nice way of thinking and programming. Okay, now that we deleted, now that we traversed through the nodes that are closer, that are leading to our target, let's see if we have our target. So it's case like here that we need to delete 3. So else we need to delete 3. Okay, so there are multiple cases. How can we delete 3? If we have so if 3 has no child or one child, then it's easy, then we just put that connection. But here 3 has 2 children, and we have to decide what we are going to do, and usually you choose node to change 3 to is in the right subtree, the leftmost child, so in this case it would be 4, or in the left subtree, the rightmost child, so again 2. And in my case, I will take from the right subtree. And how am I going to do it here? Let me think about it. So okay, so for sure I need to search for rightmost. And one thing also to note is if I do not have, or let's do it like this. So if root dot right does not exist, so if there is no root dot right, so if this one does not exist, I always return this one or nothing, independent if there is something here. So we can just return here root dot left, and this will automatically update our 3 here. Also the same thing, so if we have root dot right, if not root dot left, and we have root dot right, we just return root dot right. I think that's, and now we have to find, so if we have both of them, this is the case where we had 1 or no. And if we have both of them, now we need to update, we need to find the leftmost child in the right subtree. Mouthful. Okay, how do we do that? So current is equal root dot right, while current is equal current dot left. So we go to the right subtree and we update our current until we have this. and why maybe I didn't describe it, but so we can always maybe is there any other example? Well, this is the best example actually. So imagine we have to delete 5. If we have to delete 5, we don't have to do any change if we take the smallest value here in the right subtree or the biggest value in the left subtree. So we can directly, if we remove 5, change it with 4 or 6. 6 is the smallest value here. So if we change it by 4, it's 4, 3, 6, 2, 7. If we change it by 6, it's 6, 7, 3, 2, 4. So everything is the binary search tree property is still intact. So yeah, let's now do the letter part. So we found our leftmost node in the right subtree. Could be 6 or could be something down the line. And now we need to update the node we have to delete with value with current dot value. Okay, okay. And now the last thing is to delete that extra node. So to delete that extra node, we just have to update. So our root dot write. So potentially it will be the first node. So we have to delete essentially it and update our connection. Delete node root dot write and current dot value. So why did I put root dot write here? Because our root value is essentially the same. So we could first do this and then delete it, but yeah, never mind. This is also good. This is like safer, let's say. So yeah, this should be it. So pretty interesting. Let's see, let's run it to see if it's working. And it's not. Solution delete. Okay, this is typing mistake. Wow. What? If not root right, return root left. If not root left, return root right. Current is root right, while current okay, this is a mistake. While current left, current is current left. So as you can see, yeah, this would never work. So this is the right approach because I tried to I went through with current up until I had nothing. So yeah. Okay, so seems to be working. I'll just submit it to be 100%. Yeah, it works. And now let's once more check it out. So I think it's clear, but it's nice to have it like all written and once more understand it. So when we delete the node, if we have nothing and we want to delete something, we just return that nothing to the call above to keep because we will traverse the nodes to find it for the BST, but if we came to nothing, that last connection led us to nothing, and we always update that last connection, so that's why we return root here. So if root value is greater than key, so if we want to delete something that is smaller than our current root, then we need to go to the left subtree and try to delete node there. and in the end we return the same root that we had. Okay, the same thing goes for the right side, but if we found a node, if we don't have nothing to the right, we can just delete the node the way that we return what that node that we are trying to delete has on the left side. If it's nothing, that level above will be updated with nothing. If it's something, it will be updated with something. So that's the easy case. Same thing for the other side. But if there are two children, we need to find either the leftmost child in the right subtree or the rightmost child in the left subtree, because one is the highest value on the left side of the tree and the other one is the lowest value or the smallest value on the right side of the tree. And when we find it, so this I'm finding here the smallest value on the right subtree, we take the value and we essentially delete the node that we just used for updating our root. Okay, I hope it was clear. I had a lot of trouble with this one, so it's nice to understand it completely and be able to code it up. Space complexity, so recursive calls, well, log n best case. If it's queued, then it's n, but I'll keep it log n for both of them. Let's see if I can check the complexity. Our server is still busy for my requests. Nice to see that I'm getting my money worth, as they say. Okay, yeah, that's all I got for this one. If you have any questions, leave them in the comments. I appreciate you for following and see you in the next one.